Good morning. My name is Keith Hare, and I'd like to spend a few minutes today talking about replicating RDB databases with the JCC LogMiner Loader. The LogMiner Loader supports replicating committed transactions from RDB databases to other databases using a variety of transports such as the RDB mechanisms, the Oracle OCI, and JDBC drivers. In this session, I want to provide a detailed example of setting up replication to a Postgres database on a Linux server. I'm also going to describe how to use a new JCC LogMiner Loader feature that will be available in a future release soon. The topics I want to cover are the overall goals of replicating data, the big picture of how all of this works, what you have to do to prepare the source database, what you have to do to prepare the target database, how do you go about setting up the JCC LogMiner Loader. Once you have it set up, how do you monitor replication to see what's going on? And then once you get everything working, there are all sorts of other questions such as what about this and what about that? And I will address some of those, and finally I'll provide a summary. The data replication goals are generally to make RDB data available in some other environment in near real time in a transactionally consistent manner. This could be the target could be a reporting database, could support ad hoc queries, could support a website or testing or audit, or whatever needs you have for replicating the data. First, the big picture. You have an RDB database, the source database, and you've got some target, and you need to somehow get the data there. You have processes that are updating the source database, and the data is being written to the live afterimage journal files. The RMU unload/after, the continuous logminer command, can extract data from the live journal and output it to a variety of output devices. In our case, we use OpenVMS mailboxes. The LogMiner Loader reads the data out of the mailbox and applies it to the target. Of course, we have some configurations that we have to set up an options file to tell RMU-CLM what to unload, some control files to describe the data that we are going to get from RDB and what we're going to do with it, a control process to manage the whole thing. You might have you're going to back up your AIJs periodically. To back up, then we need to be able to handle that, and we need to be able to restart. So this whole picture is what we refer to as the continuous LogMiner Loader. The source is going to be an RDB database, and it can be any version that supports the LogMiner, which is RDB version 7.0.6.5 or later. The target can be another RDB database. It can be an Oracle database using SQLnet. It can be a JDBC. You can use a JDBC class 4 driver. The advantage of a class 4 JDBC driver is that it runs completely in Java, and so you can run it on any environment where you have a Java runtime engine. We also support Tuxedo, or can write XML to your own API, or we can write to an output file. The sources and the targets can be both logically and physically different. The tuning can be different, the indices can be different, the placement, buffering, caching, and can be completely different databases. In this example, we're going to use RDB version 7.3 for the source database running on an Alpha VMS 8.4 system. The source database is a virtual ES40 running on one CPU and 1024 megabytes of memory, so a relatively small system, but we don't have a big workload. The target system is a Postgres version 9.4.4 database running on a CentOS version 7.1 Linux. This is running on a virtual x86 with 2 CPUs and about 6 gig of memory. And the advantage of this configuration is that I can run both of these virtual machines on my laptop, and so can do testing in this environment any place I happen to be. The source database, it's best if you're running a recent version. If you're going to use JDBC, then you have to have a Java implementation on your system, and so there are some requirements there. You need to have circular AIJs enabled, you need to have continuous LogMiner enabled, and you need to have immutable primary keys. And I'll come back to that in a couple slides. Here's an example of creating an afterimage journal. Reserve 10 journal slots, create the journal files, enable continuous LogMiner, and finally enable the journaling on the database. The idea of an immutable primary key is that we need to know what we can use to locate the record in the target table so we can update it. What we get out of the LogMiner, the RDB LogMiner, is what the data looked like after the update occurred or before the delete occurred. But if you update the primary key, the logical primary key, in a transaction, we don't get the before version of the primary key, and so we can't find the original record on the target. So we want to have a primary key that doesn't change on the source database so that we can use it to replicate the changes to the target database. If you don't have one in your environment, you can use an SQL identity column on the source tables to accomplish this. The target database, we need to have a primary key and indexes on the primary key. In some databases, when you define a primary key, an index is automatically created to support the primary key. In other databases, the idea of a primary key and an index are separable. So you need to understand in your environment whether or not you've got the indexes to allow things to perform well. If you don't have an index on the primary key field in the target, when you do 10 rows, it's going to perform just fine. When you do 10 million rows, the performance is going to degrade quite a bit. So I'm going to talk about creating the tables in the target, show you an example of querying the data with Postgres, and how to look at Postgres, look at the tables using Postgres on a system. Once you get Postgres installed, you invoke the command line SQL with the PSQL command, and you exit with the /q. Postgres SQL looks a lot like RDB SQL. So you can do a create table, and in this example, the create table and the add constraint were originally created with an RMU extract /item equals all from the source database. You can query the data with an SQL query that looks a lot like what you would do on RDB. To describe a table, you use a \d in the table name that shows you the columns and the data types and the indexes and keys. To set up the LogMiner Loader, you need to have a JDBC driver on VMS. You need to have an options file, and a configuration file, and a command procedure that puts everything together. To get the JDBC driver to open VMS, I downloaded it, and on my Windows machine I renamed the file and replaced periods with underscores, and then FTP'd that to the OpenVMS system. In this case, I have an ODS5 disk which supports lowercase file names. Now, anytime you FTP a jar file, a Java jar file to VMS, you need to reset the file attributes with the set file attribute command I have here. I include this anytime I'm doing a presentation like this because I don't remember the syntax, so I just need to remember where it is I have examples of the syntax. So which Postgres JDBC driver should you use? According to the Postgres documentation, if you're using Java 1.7 or 1.8, then you use the JDBC 4.1 jar. For Java 1.6, the JDBC 4, and Java 1.5, you use the JDBC jar. On Alpha OpenVMS, the latest version of Java is 1.5.0-8. And since I'm running on Alpha, that means I'm going to use the JDBC 3 jar file. On Itanium, the latest version is 1.6.0-6, so I could have used the JDBC 4 driver if I'd been running on an Itanium. You can generate the options file you need with the command JCC create LogMiner opt file, and you point it at the database. In this case, MFP_v73 as a logical name that points to the appropriate database. The option file tells the RMU unload/after/continuous command which tables to unload. In this example, the exception message occurs because I haven't added some additional functions to the source database. But the only reason I would need these functions in this case is if I wanted to always eliminate a set of tables. And it's not an issue in this small example. The options file only needs to be regenerated when tables are added. So it lists a set of tables and an output. In this case, the output is RDB LogMiner output file. That's a logical name that we'll set up later in our command procedures, and it's going to point to an OpenVMS mailbox. If you read through this carefully, you'll note that I've commented out the table resumes. The table resumes in the sample personnel database contains a column that is a segmented string. The RMU unload/after command does not support segmented string data types, and so there's nothing we can do with them because we don't get them at the loader interface, and so we can't do anything with them. You can use the JCC LML create control file to generate three types of files: a table file, a map table file, and a date filter. The table file describes the source tables that we're going to get from the afterimage journal. The map table maps those source tables to tables in the target database. The date filter I'll come back to in a second, but it's useful if the source might have bad dates. The table file describes the source data. It includes the table name, it includes the columns for each of the tables, the ordinal position, the data type, and so on. It would be possible to generate this by hand, but you really don't want to. One of the things in here is for each table is the table version number. So this file has to be created anytime you do anything to the source data that's going to create a new version for the table, such as adding a column, dropping a column, changing a data type, either directly or by changing a domain. The map table says that this source table maps to a target table. If all of the table names and the column names in the target match the table names and column names in the source database, then this is relatively easy to do. If you have different table names or column names, or you're working with a database as a target that is case sensitive, then you may need to do some editing of this file. In the bottom of this example, we have a map key that says that the key is the originating DB key. In the source database, this table did not have a primary key. And so we're going to add a column to the target that is the DB key of the original record. Here's an example for the employees table, where the key for the employees down at the bottom is the employee ID. And we were able to pick this up from the primary key constraint in the source database. If you have primary key constraints defined in the source, you have much less editing to do on the map table file. You may need to correct the primary keys. If the column names have changed, you may need to change them. The map key specifies a logical primary key that's used when we do an insert or an update into the target, or a delete in the target. And it's generated based on either the primary key constraint on the source or a unique index, or otherwise we assume that you're adding originating DB key to the target. The originating DB key can be used as the target. In RDB, this is a physical address for the source record, so it's guaranteed to be unique within a database. In the target, you're going to need to use an 8-byte integer for this data type in the target database. The one potential risk of using originating DB keys is that if you reorganize the source table somehow using an RMU unload, load, or an export import, then the target table must be completely reloaded because the DB keys, the original DB keys, will have changed. The date filter file we added in support of clients who frequently had bad dates. The OpenVMS date data type supports dates well past the year 9999. However, the date formatting functions only support 4-digit years. What this function does is, or what this filter map does, is to filter out anything with a date outside of the range of valid VMS dates. It's optional, but it's useful in some environments. The reason we added this is we had some clients who had some code against the source database that would frequently overwrite garbage into a date data type. And so rather than generating an exception every time we ran into that, we allowed them to just filter out those particular dates. In the case of Postgres, most RDB data types have corresponding data types in Postgres. There are a couple of data types that we need to change in this example. For scaled integers in an RDB database, we needed to use a number data type in the target or a money data type. For VMS date in the source database, we used timestamp 2 data types in the target. So we've set up an environment. We need to set up an environment with the JCC LML user and the JCC LML JDBC user commands, set up some logical names, and this is going to be in a file that I'm going to call mfp_postgres.com. And then what this is going to do is to invoke the JCC run CLM LML command with 3 parameters: a pointer to the database, a logical name of the database, the options file we created a few slides ago, and a INI file that has some information about the target and includes the personnel, the table INI file that we created that describes the source data, and the map table INI file that maps to the target data. So this command procedure is going to look like DCL, where we start off by setting up our environment with the JCC LML user command, setting up Java for the environment, defining some Java command lines, specifying the loader name, specifying the NLS language, although it turns out that in this case this line is specific to an Oracle interface, and so it doesn't make sense in the JDBC interface. We tell it where backed up AIJs are going to be, and tell it what to do when we run into old versions of tables, and then point it at the database, the options file, and the INI. The INI file has some information in it about logging, information about a checkpoint, and information about the JDBC driver, where the target is, what the driver name is, how we're going to log into the target, and where to find the driver file. And down at the bottom, we've got the includes I was talking about, where we include the MF personnel table.ini and the map table.ini. One of the hardest things when working with JDBC is to figure out the correct connect string. So you have to go looking through the documentation to find that for Postgres, the connect string is JDBC : PostgresQL. The target in this case is an IPv4 IP address 192.168.27.22. That's the Linux machine where I have Postgres installed. The default port is port 5432, and the database name I created on Postgres is called Keith. So I have a command procedure that sets up some things, starts up the LogMiner Loader with some configuration files, and I set this all to work by submitting it to a batch queue. When I have everything working, there will be 3 or more processes. In the command procedure, I set the loader session name to kwh_Postgres. And so I have a CTL process, which is the control process, a CLM process that's reading from the source database, and then in this case I have one thread process that is writing to the target database. And I'll come back to the concept of threads later on. So I've got the loader session running on Postgres. I type a command, select stuff from work status. On RDB, I did a select star, and then I did an update work status and set status type equals status type. The effect of this is that nothing will change. The table after I do this update will be exactly the same as the table before I do this update, but because there was an update, records get written to the after-image journal file. So this is what we call a no change update. As soon as the transaction is committed, the RDB LogMiner extracts the committed data from the after-image journal, outputs it to the mailbox, the loader reads it, and applies it to the target. So within a very short time, I have the data in the target. How long will this time be? Well, it depends on a couple of factors. It depends on how big your source transaction is. If you are updating 3 rows, it's going to be very quick. If you're updating 3 million rows, it's going to be somewhat longer, because the LogMiner has to extract the whole transaction before it starts passing it on to us. The loader session creates a number of log files. There's the log file for the main command procedure that we submitted to batch. There's a log file in JCC tool logs called run CLM. There's another one called run LML. The logging information is useful when understanding what went wrong. What you need to do is to look at the first exception in the log, not the last. So when things start going wrong, all sorts of other messages end up being omitted. So you have to find the first one to figure out what happened first. JCC LML support will usually ask you for those logs when you email us a question. Once you have a loader session up and working, you can monitor it with the LML statistics command. It takes a number of parameters: the loader family name, the refresh seconds, the type of logging, and you can also notify an operator class, a VMS operator class, if things are running long. In this example, I'm going to just use the loader name, KDBH underscore Postgres. I'm going to refresh at 6 seconds, and I'm going to use the detail statistics. So every 6 seconds, a screen that looks like this will paint on your output device. The left side describes the input data. The right side describes the output data. So in this case, on the input, we've gone through 1,400 source transactions with 14,000 and some odd records. We have about 2,800 rows that were modified, inserted, where a modify is an insert or an update, and 10,100 rows that were deleted. We also have done this in 1,424 transactions, so we have commit records. The output has output approximately 1 commit on the output for each commit on the source record. And we've sent 12,000, almost 13,000 records to the target. In the bottom right corner of the detail display, there is information about the most recent interval and information about the latency. In this case, we're spending about 50% of our time waiting for the target. This is relatively reasonable in my experience. If we see that we're spending over 90% of our time waiting for the target, then we need to understand what's going on in the target. We've seen cases where somebody neglected to create an index on the primary key, and once you get over 1,000 or 2,000 rows, it takes longer and longer. When you get to 1,000,000 rows, it takes a really long time anytime you update the target. But now that we have everything running, what about shutting it down and restarting it? What about adding additional information? What about filtering? What about transforming? What about multiple update threads? How do we verify that all the data is in the target? And what additional targets could we use? Shutdown is easy. The command is JCC CLML shutdown. And you give it the loader name, and that shuts everything down neatly. Restart also is easy. On Oracle and RDB, we maintain a high water table in the target database that has the information about where we need to restart. For JDBC, we have a checkpoint file on the source system. And what happens is, right after we commit to the target, we update the checkpoint information on the source database. In this case, I've defined a logical and pointed it, the checkpoint to loader checkpoint Postgres underscore MFP. We can guarantee that all committed transactions will be replicated to the target database. However, a restart may resend some transactions, and there's a variety of reasons why this is true. I'm not going to get into the details today, but you have to remember that when you're setting up a replication using our tool. You can view the restart information with the dump checkpoint command, where you pass it the loader name, the name of the checkpoint file or the target database, and the type of the checkpoint stream. the type of the checkpoint file. So in this case, I'm dumping the checkpoint file, loader checkpoint Postgres, and it's what the type we call LML internal. That is, its structure is internal to the LogMiner Loader. It's not stored in a database. And this contains a number of pieces of information, and it's actually the AERCP at the bottom that gives us the information about the restart, about where in the afterimage journal to restart. We can add additional information. We can add a variety of virtual columns that don't exist in the source database. We can add originating DB key, loader sequence number. We can add the transaction start time and the transaction commit time. We can add the process ID of the open VMS that performed the transaction in the source database. So you can actually use the loader to begin to get information about how long the source transactions are and what process IDs are actually doing the updates to the source database. We can also add virtual tables, so it's possible to map commit information to a table in the target database. We can filter data using the filter map clause. The example here comes from the earlier example of filtering out bad dates. The filter map statements must be in your configuration file after the map table statements. And it looks a lot like RDB SQL. And the reason for this is that it's processed using dynamic SQL against a database we create called the filter map database. A filter map statement can only reference the current row. The filter map database is created specifically for evaluating filters. The default is it's going to be in JCC tool data with the name of the loader name. We have several logical names: the LogMiner Loader filter dir and the loader filter name that override these defaults, so you can specify where you want to put the filter database. The filter database is automatically created when it's first needed. You could create your own filter map database if the defaults are somehow not sufficient for your environment. I've got an example here of the parameters we use on the filter map database. We support some sorts of transformation. You can map one source table to multiple target tables. You can map multiple source tables to one target table. You can turn specific values into nulls. You can turn nulls into specific values. But what if we could add a function to the filter map database? In some future release, we will support the ability to add a function that processes the data that we pass to it. In this case, we've created an example function called DB key to text, and it takes the originating DB key and it turns it from the 8-byte integer structure into a character string format. It's added as an external function in the filter map database. You could also use RDB functions there, and we're working on testing that and hope to be releasing it sometime. In this example, I'm updating some columns in the I'm doing a no change update on the source database, and I've added a text DB key column to the target database. So I've got the originating DB key, which is a big int, and the text DB key, which is a character string showing the text format of RDB DB keys. If you've worked with RDB, you've probably seen DB keys that look similar to this. Sometimes there are a benefit to sending data to the target database in parallel streams. In this example, I've configured it so that I can have 1 to 4 concurrent update threads against the target. The A thread will start up if data is available for more than 10 seconds while all the other threads are writing, and a thread will shut down if it's idle for more than 30 seconds. You need to be cautious with doing things in parallel, because if one thread overwhelms the target database, then adding an additional thread is going to overwhelm the target database more. We also check to see if one thread contains data that is already being written by an existing thread. And that's what the constrained option is. And that can increase the amount of locking that your system, the number of lock operations on your system, which adds to the overhead. So it's a useful capability, but it should be used carefully. There are a lot of challenges in comparing the data in two databases. The data representations might be different. You might have char in the source database and varchar in the target. The floating point data types might have different representations. Date time and timestamp precisions might be different. If you have only a few records, then doing the comparison is easy. If you have millions of rows that you're replicating, then it takes more time to do the comparison. One of the questions is, can you freeze the updates while you're doing a compare, or do you have to do the compare as you're continuing to update the target database? We actually have spent a lot of time doing verification of data between the two targets in our test environment, but the techniques by which we do that really end up being beyond the time that I have in the session today. RDB targets are very straightforward. Oracle targets require the Oracle call interface. One of the biggest challenges is getting the Oracle client installed on OpenVMS, and you have to understand the data type differences. With JDBC targets, it depends on the JDBC driver and what the target characteristics are. You have to capture the driver files and copy them to VMS, reset the file characteristics. You have to specify the appropriate class path and the connection string, and you have to understand the data type differences. But it's quite possible to do this. Our experience is that setting up the first loader session against a target takes the longest. Once you get the first one set up, it's relatively easy to move on to a new session and create a new session that's similar. Okay, what we've tried to do in this session is to discuss what it is that the LogMiner Loader accomplishes and to present a detailed example of setting up replication, in this case from RDB to OpenVMS to Postgres on Linux. And you can use this as a base for understanding what you need to do and how to set up a loader session in your own environment. We also hinted at some additional LogMiner Loader capabilities in a future release. In all of this, we've worked closely with RDB Engineering, and I'd like to thank them for the support and counsel. And we'd also like to thank our customers for telling us about what they've done with the loader. What we find is that our customers end up doing things with the JCC LogMiner Loader tool that are really interesting that we had never actually thought of when we were building the tool. And of course, join in the RDB mailing list. It's a relatively low volume mailing list with RDB people all over the world. And are there any questions?